spring force. Okay, this is otherwise known as Hooke's law, named after Robert Hooke. Here's the equation as it is written on your AP equation sheet. Okay, here the absolute value bars mean the magnitude of the vector. Okay, so the magnitude of the force, all right, exerted by a spring is going to equal K times the absolute value of X. Okay, here K is the spring constant, all right. The more frequently known units from what we studied previously, okay, are newtons per meter. So it's how many newtons it takes per meter to stretch that spring. So the stiffer the spring, the bigger the K value. It's going to take more force to stretch it. And K is unique to a given spring, okay? Each group probably got a different K value today in the lab because they used a different spring. X is the distance from the equilibrium position, okay? So what we called stretch in our lab, okay? This is not the position, this is almost more of a change in position, okay? So if the equilibrium position for the spring is where it wants to be, okay? So initially when we didn't put any weight on it, okay, that was 0 for the X, so there was no force exerted by the spring. Now, if I put a weight on it for it to be at equilibrium again, okay, the force that the spring exerted equaled K times that distance.